remind you at the end of yesterday's lecture, we introduced the Cantor-Ovich problem of optimal transportation, which was to minimize the integral over the product space of a cost function among all joint measures with fixed projections onto m plus and n minus. And we observed that this was a convex set of measures, and this was a linear functional in that convex set. And the convex set was non-empty because, on the one hand, product measure was in the convex set. And on the other hand, if there's a Monge map, which is not clear, but if such a map exists, which pushes forward the first measure to the second measure, then I have a map from M plus into the product space given by, let's call it identity cross G. So it takes x to the point x comma g of x. And I can push forward this measure mu through this new map. And that will define the measure gamma. And it turns out that this gamma belongs to this set if and only if this holds. So wherever I have a candidate in Monge's problem, I have a candidate in Cantor-Ovich's problem, but not every candidate in Cantor-Ovich's problem comes in from a map G. Like, for example, this one doesn't. So generally, mu cross nu is not equal to identity cross anything for any H. So somehow I'm trying to minimize now in a bigger set than I was before, because all of these guys are in here, but not all of these guys are at that point. And so in some sense, this bigger set, it helped me show that the minimum attained because the bigger set was compact and the functional was continuous. And then I can go back and ask, now that I have an object like this, is it really one of these guys or not? Does there exist some G? And so the first half of the lecture today we'll be talking about conditions under which the minimum is necessarily of this form. And one of the conditions was the hypothesis that I stated yesterday in Bernier's theorem, which was special to the cost C of xy equals 1/2 x minus y squared, or equivalently minus x dot y. So if I expand this cost here out, and then I think about the thing I'm minimizing, because this term doesn't depend on y and this term doesn't depend on x. This is the same thing as and since there's a minus sign here, the min becomes a max gamma. So these first two terms don't depend on gamma at all, and only this part of the cost depends on gamma. So minimizing this is equivalent to minimizing that. Oops. So in this special case, I said that Bernier's theorem tells us indeed the minimizer is unique, and it takes this form, and G is gradient of a convex function. And I would like to start out by giving you some intuition about why that should be true. That was Bernier's result. So there's a characterization of the optimal gamma that looks the following way. So let me introduce some notion. A subset S of the product space is so-called C-cyclically monotone if whenever I choose k points in the set for any integer k, then I get an inequality that says these points, these y's are better pairs for their x's than any other y's would be. So this should imply that if I'm supplying these factories from these mines, the cost is as low as possible. So I expect an inequality like this. If I permute the x's with respect to the y's, the sum of the cost should be larger. So this is for every permutation sigma on k letters. So what this notion has to do with the minimizer in that problem is that recalling that I'll call S the support of gamma if it's the smallest closed set of full mass. So there's a characterization of optimality in the Cantor problem in terms of this notion of C-cyclical monotonicity due to Smith and Knott, which says that this thing attains Cantor, which is minimum. In other words, it's optimal for the cost C, if and only if. And so let's say for this theorem, I'm assuming that the cost function is continuous and bounded. If and only if support gamma is C-cyclically monotone. And for us today, I'm only going to try to motivate one direction of this if and only if. I'm going to try to motivate this direction. So this is the one I'm going to try to motivate. So what's the idea? Suppose I have a gamma and its support is not C-cyclically monotone. So I'm in the product space, m plus cross m minus. And suppose I can find some sequence of points, x1, x2, x3, and so on up to xk, and corresponding y1, y2, and so on up to yk. And I discover that actually this x would rather be paired with that y. And this x would rather be paired with that y. And this x would rather be paired with that y. So if the sum of the costs, so C-cyclical monotonicity would say that the sum of the costs of the x's is less than the sum of the costs of the arrows. And if support of gamma is not C-cyclically monotone, that would imply I can find some sequence like this such that there exists xi, yi, and sigma such that the sum of the costs of the xi's, yi's is actually bigger. The inequality goes the wrong way. So it's actually bigger than the sum of, let's say, xi plus 1 yi. So this would be the sum of the x's, and that would be the sum of the o's. And so what can I do? Well, the x's here are supposed to be in the support of gamma. And so that means I can take away a little bit of mass at each of these 3 points from gamma and still have a non-negative measure. And I can put down a little bit of mass at each of those 3 points. And if I'm careful about how they do this, I can subtract this mass and add that mass in such a way that I don't change the projections, either horizontal or vertical. So I can make this exactly cancel that, and this also exactly cancel that, and I change neither the horizontal nor the vertical projection. So then I create a gamma epsilon, which is approximately gamma plus epsilon times something near the sum of the x's, something near the sum of the o's minus the sum of the x's. And when I look at the cost of this gamma epsilon, because of this inequality here, I see that the cost of gamma epsilon will be less than the cost of gamma. Remember that the cost is a linear functional, so the cost of gamma epsilon is going to be equal to the cost of gamma plus this correction, and this correction is cheaper. And that implies that, whoops, this thing was supposed to be in the joint of the product. It was supposed to have the correct marginals, and that implies that gamma is not optimal. So that's one direction of this if and only if statement. I'm not going to talk about the other direction, but let's persist with it a little bit. If I come back to the special case that was of interest to Brenier, it turns out that for this special case, C cyclical monotonicity is also called just cyclical monotonicity without the C. And it turns out that cyclical monotonicity is a kind of integrability condition. So taking C to be minus the inner product, S is cyclically monotone. If and only if whenever I take a sequence, the sum as I counts from 1 to k of the inner product of xi plus 1 minus xi, yi is non-negative. Actually, perhaps I'd rather write it this way. Right. With the convention that x0 is xk by convention. And this is supposed to look very much to you. I mean, if I think about, this is a discrete version of a continuous statement, and the continuous statement would be saying that if I took a continuous curve at x's, and recall, if I have a mapping, let's say, y tilde from Rn to Rn, and if you integral around any closed curve of y tilde of x of t dotted with x prime of t happens to vanish, then y is the gradient of something. This is what's called a conservative vector field. And whenever I have a conservative vector field, should have asked for this mapping to be maybe, or I don't know, continuously differentiable or something, at least continuous. Let's say C1. And then you will, however many derivatives I have here, I get one more derivative for u. So this looks very much like a discrete analog of this condition. This here would be like delta x. And this would be y. And if I have this discrete analog of this condition, it turns out, without assuming any regularity on the set S, that in fact, there is again a function u associated to the set S, such, and u will be a convex function now, but it won't necessarily be smooth. But in some sense, the derivative of that function is going to contain S. So this is a theorem of Rockefeller from the late 1960s. This is another if and only if statement. There is a convex function u such that S moves inside what's called the subdifferential of u. And what I mean by the subdifferential of u is the set of all points x and y, such that the first order Taylor expansion of u gives a lower bound. The first order Taylor expansion with slope y right? So normally in a Taylor expansion you'd have an extra error term. This was lousy notation. For convex functions, it turns out that if this linear function is less than the function, then the error term is 0. So this thing here is the set of point slope supporting hyperplanes to the graph of u. But in case u happens to be differentiable, this would be exactly the graph of the gradient of u. So if it's differentiable, then there's exactly one y, which can satisfy this at every point x. And then this object here would be the graph of the gradient. And so this theorem of Rockefeller's is exactly a discrete analog that starts from this condition of this familiar theorem from multivariable calculus. It tells us when is there a potential whose derivative contains the set of interest. And so now we can sort of see why Bernoulli's theorem ought to hold. You know, I take the minimizer for the Kantorovich problem with this cost. Smith and Knott's argument tells me that the support of that minimizer has to be cyclically monotone. Rockefeller's theorem tells me that the support is then contained in the graph of the gradient of a convex function. Okay. So you can actually make an argument like this work for more general costs, but maybe it's more interesting for me to show you another technique, which is very general, and it's based on the duality theorem of linear programming. So we started out by observing that Kantorovic's problem was a linear program. The other thing with Kantorovich, maybe you should actually push it forward, because then I'll be behind it and it shouldn't feedback so much. I turn it off for a moment. So we'll give that a try and see if that's any better. So the other thing Cantor discovered in 1942 was he discovered linear programming duality, at least for the special linear program that he had formulated. And I guess the general version was discovered about 5 years later by von Neumann. So Cantor, of course, he was looking at costs to satisfy the triangle inequality, but I'm going to state a version that works for more general costs. Cantor showed that actually the minimum of the integral of the cost d gamma on the product of m plus and m minus over all gamma, the value of this minimum, the thing we called W the other day, is also given by some maximum, or at least a supremum, and it's the supremum over pairs of functions u and v in a set I'm going to call lip C, and then we have the integral of u against nu and the integral of v against nu minus rather. And I have to tell you what is the set lip C. So the set lip C is let's say L1 functions with respect to the measures in question. But the crucial thing about them is they should satisfy the inequality that C of xy is always bigger than u of x plus v of y. Well, that looks like a sort of surprising statement at first. Again, one direction of this inequality is easy, so this one's kind of easy. And the miracle is that equality holds, but let me show you the easy direction.
Is there any reason why you're putting minus in front of u and v?
Yeah, so I have an annoying sign convention that makes the regularity theory more natural, at least to me. So in the end, I prefer to deal with convex functions rather than concave functions. Are there other questions? Yep. Yeah, sorry. Thanks. So that was the question? Yeah. Well, so there's a little, I'm cheating a bit with my notation. So u plus is negative v and u minus is negative v. That's my notation. Thanks. Is this one going back? Thanks. So how does the easy direction go? Well, suppose, so let gamma have the right marginals, and a pair minus uv be in lip C. So for minus u and v to be in lip C, it means exactly that C of xy is bigger than minus u of x minus v of y. And now integrate this, that's the definition of lip C, integrate that statement against gamma. So when I integrate that statement against gamma, what I get on the one side is integral of C d gamma over the product space. Now I integrate this against gamma, u doesn't depend on y. So when I integrate this against gamma, I just see the integral of u against u plus. And similarly, this thing doesn't depend on x, and so when I integrate that against gamma, I see the integral of v against mu minus. And now this inequality here holds for everything in this set and everything in that set. So in particular, I can minimize on the left-hand side, since it holds for everything in this set. And it still has something larger than this for any UV over here, and I could also maximize on the right-hand side. Right, so that's the easy direction. And again, the remarkable thing is that equality holds here. And so I'll try to give you some intuition for why you might expect equality hold. And the intuition that I want to give is based on the theory of two-player zero-sum games. So we're going to have a little excursion into, and also von Neumann's minimax theorem for convex concave functions. So what happens in game theory is, at least in two-player zero-sum game theory, is you have player one who has a certain number of strategies that he can choose from, and player two that has a certain number of strategies that he can choose from. So P1 chooses some strategy X in a space capital X, and P2 chooses a strategy Y from some other space capital Y. And then they compare strategies, and player one pays player two something, depending on which strategies were chosen. So there's a payoff function, capital P. It's known to both players in advance, and player one would like to minimize the payoff and pay as little as possible, and player two would like to maximize it. So P1 wants to minimize, and P2 wants to maximize. And naturally, it's an advantage in this game if you know what strategy the other guy is going to choose, because then you can adapt your response. And so because it's a disadvantage, to be forced to declare your strategy before the other guy has chosen. It's easy to see for this reason that if so for example, player one wants to minimize. If player one has to declare its strategy X, and then player two is allowed to choose a strategy Y, that's going to be better for player two than if player two has to first declare his strategy Y, and player one then chooses his strategy X, because if I'm player one and I know Y here, then I can choose X to minimize the payoff. And so the result will be that player two will try to maximize the minimum payoff that player one gets by reacting to his strategy, but he won't do as well as if player one has to declare the strategy first and then player two gets to maximize, in which case player one will try to minimize. So there's a natural inequality between the imp soup and the soup imp. And the question that von Neumann addressed was, when can I expect equality to hold here? So this inequality holds with almost no structure on P or XY. And von Neumann's theorem said, well, let's assume capital X and capital Y are compact convex sets, and if the function P is continuous and convex in the variable you're trying to minimize and concave in the variable you're trying to maximize. And then I can expect equality to hold. So this was von Neumann's min-max theorem. So if I fix any point in the product space, the functions so x is trying to minimize, so von Neumann assumed that this function would be convex, and y is trying to maximize, so von Neumann assumed the negative of this function would be convex. Then equality holds here. And it turns out that the equality here is kind of, it's sort of like a special case of von Neumann's theorem, except I'm in an infinite dimensional context, so I'm not in Rn, and I don't have the compactness. I mean, somehow sort of the geometrical structure for this is right for that, and the topological structure is wrong, but still the intuition that it conveys is the correct one. So let me tell you a little bit about how von Neumann proved his theorem, and then we'll come back and see how it's related to counter-image duality. So let's do a sketch of a proof. And for simplicity, let's assume the convexity of the functions p is strict. Right? If not, then I'm going to first do perturbation. Instead of I'm going to add epsilon x squared and subtract epsilon y squared from p. Then the convexity will be strict. I'll prove the theorem for p epsilon, and then I'll let epsilon go to 0. Right, p is supposed to be continuous here, so. And so as long as the convexity statements about p are strict, then the best response functions of player 2 and player 1 defined by, so y should be player 2's best response to strategy x, so that's the maximizer over all y of pxy, and xb will be the minimizer, player 1's best strategy response to strategy y. Sorry, this is capital X rather. If the convexity in X here is strict, the minimum will be uniquely attained. And if the minimum is uniquely attained, then when I move y a little bit, x v of y isn't going to go too far. So these best response functions defined this way will be continuous functions. Are well-defined and continuous. Right, xb takes y into x, and yb takes x into y. And so I can look at the composition of these two functions. xbyd takes y into itself. Or it takes x into itself, rather. And X is a compact convex subset of some Euclidean space, so it's essentially a disk of dimension at most n. So, at least topologically, closed disk. And so whenever you have a continuous map of the closed disk to itself, Brouwer's theorem tells you it has a fixed point. So Brouwer's theorem says that there exists some x naught, x star, let's call it, in x, such that player 1's best response to player 2's best response to strategy x star is x star. Fixed point theorems are very useful in partial differential equations. So let's call set y star to be yb of x star. And then what I observe is that xb of y star is equal to x star, and yb of x star is equal to y star. So what Brouwer's fixed point theorem has found for me is a pair of strategies x star and y star, such that even if player 1 knows that player 2 is playing strategy x star, player 1 can't do any better than playing strategy x star. And even if player 2 knows that player 1 is playing strategy x star, he can't do any better than y star. So this is what's called a Nash equilibrium. When player 1 plays this and player 2 plays that, neither one of them has an incentive to change their strategy, even if they know what the other guy's doing. So that's a Nash equilibrium. And geometrically, what that corresponds to is kind of a saddle point in the function p of xy. So the geometry is a little bit, if this is x and that's y, the geometry is that we're at a minimum varying x and a maximum varying y. So this point here, x star, y star is kind of a saddle point. And so how do I see that? Well, p of x star, y star, since this is player 1's best response to that strategy, that payoff is less than or equal to the inf over all x of pxy star. And since this is player 2's best response to that, and player 2 is trying to maximize p, that must be bigger than the sup over all y of px star y. And on the other hand, this is some particular x star. This quantity only gets bigger if I take a it's a particular y star. It only gets bigger if I take a supremum over y. And this quantity some particular x star, it can only get smaller if I take an infimum over x. And that's exactly, this chain of inequality is exactly this the opposite statement to this one here. So all inequalities must become equalities. Other questions? Okay, so I claimed that this statement had something to do with Kantorovic's duality theorem, so at least geometrically, if not topologically. So what is the payoff? What is the two-player zero-sum game? What is the payoff function for it? So the example, which is not a real example because it's going to be infinite dimensional and non-compact, but what is the payoff function? Well, the payoff is going to depend on gamma and u and v. And it's going to be something like the integral over the product space of cxy plus ux plus vy d gamma, and then minus integral of u du plus minus integral v du minus. And this is defined on gamma should be any non-negative measure on m plus and m minus. That's the set capital X. And the set capital Y should be u and v in L1 dv plus and L1 dv minus. So notice this function it's linear in gamma and it's linear in u and v, so it's bilinear. By the way, I should have said the original problem that motivated von Neumann's theorem was also bilinear. And the original problem that motivated von Neumann's theorem was the special case. So this is an honest example. Let me give you the honest example, then we'll come back to that one. So von Neumann wanted to think about a situation where player 1 had only a finite number of strategies at his disposal. So we could think about these as being like unit vectors in a Euclidean space of dimension m. And player 2 had a finite number of strategies at his disposal, which we could think of as being basis vectors in a Euclidean space of dimension n. And okay, that's a hopeless problem. But von Neumann said, let's assume the payoff. Let's assume that players are not forced to choose from this discrete set of strategies, but they can take probabilistic approaches. So they'd say, player 1 would say, I'm going to do this 50% of the time, and that 33% of the time, and these other things a smaller percentage of the time. And so if we allow probabilistic strategies, so X would be some linear combination Ti of Ei hat, where the Ti's would be non-negative and sum to 1. And similarly, Y would be some convex combination of these guys. And if we assume that the payoff for such strategies I'd have similar coefficients Sj is the expected payoff. So in other words, if it's the double sum on I and j of Ti Sj of the payoffs of the pure strategies. So these guys are given, and I construct this guy by making things linear in both variables. then this is a bilinear function. And on the convex hull of x naught and y naught would be the standard m simplex and n simplex. So those are compact convex sets. And this was exactly the situation which von Neumann wanted to show. There may not be a Nash equilibrium in the original game where we're forced to choose discrete strategies, but if we allow these probabilistic strategies, then there's always a Nash equilibrium. So there's always a saddle point for this function p of these continuous variables, even if there wasn't a saddle point for this function p of the discrete variables. So over here, in this context, we're also looking at a bilinear payoff function p, and I want to show you that when I compute the inf sup, I get this thing, whereas when I compute the sup inf, I get that thing. And so that's some kind of motivation for why you might expect this easy inequality to turn into a case of equality. So I want to compute the inf sup of p, gamma non-negative, sup minus uv in lip c, p gamma uv. So let's imagine I fix gamma non-negative. I try to maximize on u and v. Okay, to do that, it's better to rewrite p a little bit in the form I want to separate the u and the v. So I'll have integral c d gamma, that will be integral over the product space, but then the coefficient of u is something like and the coefficient of v is something like and so now I want to maximize overall mu and v. Well, if the left marginal of gamma is mu plus, then this integral vanishes, and it doesn't matter what I choose u to be. But if the left marginal of gamma is anything other than mu plus, say it's positive near some x, then I choose mu to be huge near that x, and I can make this supremum go to plus infinity. So this p is plus infinity unless the left marginal of gamma, pi 1, push forward gamma is equal to, or pi plus push forward gamma is mu plus. And similarly, unless the right marginal of gamma is mu minus, if this difference was negative at some point, I could take v to be huge and negative at that point. Or if this difference was positive at some point, I could take v to be huge and positive at some point. And so the supremum would be plus infinity. Whereas here I have in mind p plus of xy is x and pi minus of xy is y. And if both of these things are true, then these terms vanish, and this is equal to integral c d gamma. And so now that's what the supremum does. When I try to do the infimum, obviously the points where the supremum is plus infinity are not going to contribute to the infimum. And so this ends up being the inf over only those gamma non-negative that satisfy these two additional conditions. Of integral c d gamma. And that's exactly what appeared on the left-hand side here. Now I can try to interchange the sup and inf, and when I interchange them, hope at the right-hand side of what's over there. Oh, I'm sorry. I shouldn't have put lib C here, I should have put all of U and V in L1. So that I'm completely free if this thing is not 0 to choose V to make it large. Similarly, if I take the sup over all U and V in L1 in with gamma positive of P gamma UV, then if this integrand were negative somewhere, I would choose gamma to be huge at that point, and I would send this part of P to minus infinity. And so this is going to be equal to the sup of U and V in L1. If the infinity is minus infinity, it won't contribute to the sup, and so I might as well assume that the integrand is non-negative. Once I've assumed that this integrand is non-negative, I'm trying to minimize in gamma. I might as well take gamma to be 0, because gamma is non-negative, the integrand is non-negative, the smallest I can make this term is 0. And what's left over is minus the average of u against mu plus and the average of v against mu minus. And this is exactly lib C. So this is exactly the right-hand side of Cantor-Rich's duality theorem. And so now I'm in a very good situation. I can harvest a lot of consequences of this. So for example, that's the end of the motivation for why it should be true. So as a kind of corollary, suppose I have gamma, a feasible gamma and a feasible U and V, such that the left-hand side equals the right-hand side. So I could write this as an integral against gamma, and that is an integral against gamma, and bring it all over to the left. And what I would have is something like this. Right, if I can find the gamma and a UV that produce equality here, then gamma must be optimal, and U and V must be optimal in the priming problem. So if I produce equality here, then I've got the smallest I can have on the left-hand side, I must also have the largest I can have on the right-hand side. And if I knew that this is super-attained, if this is a max, then I would have the converse as well. If I knew this super-attained, then I would know that for the maximizing U and V and for the minimal gamma, this integral would equal this difference, which is to say that this thing would vanish. And i.e. gamma is supported in the 0 set of the non-negative integrand. So we're going to take a little break in a few minutes, but the strategy after the break is to show that there's another compactness continuity argument that says the supremum is actually attained, and then this kind of characterization becomes if and only if. A measure gamma is optimal if and only if you can find U and V in this set such that gamma is supported in the 0 set of this non-negative function. And so you can read a lot of things off of that. So for example, because the function's non-negative, if in addition, if, let's say I have some point xy in support gamma with x happening to be a point where u is twice differentiable. So then I have this non-negative function that I know happens to vanish if this xy. The fact that it vanishes tells me two things. Its first derivative is 0. So I have the first derivative, and its second derivative is non-negative. That's the condition for a local minimum. And for a non-negative function, 0 is always a local minimum. And if I think about the Brengier's case, the case c of xy is bilinear, then the derivative of c with respect to x is minus y, and the second derivative of c with respect to x is 0. And so this first condition here would be telling me that y is the gradient of something, some u, and the second condition here would be telling me that the u is convex. So these conditions here exactly look like Brengier's theorem. And I guess that's the point that we'll pick up with after the break. So why don't we take, I don't know, a 5 or 7 minute break and then resume.